Okay, hello guys.
Hello.
How are you doing? Okay, lecture number 10. First of all, how about exercises? Everything's fine?
Yeah.
Yep.
So did you invent something while, while working with this magnificent material mirrors? Yes?
You know how you said how, for example, let's say you aim the light,
Okay.
like in a telescope, to the galaxy Centaur,
Alpha Centauri.
oh yeah, Alpha Centaurus,
Okay.
and then you said the light would reflect back to Earth, but billions of years in the past.
Yep.
What if you use instead of using regular mirrors to reflect the light, you use the duplicator mirror to reflect the light, so that if the light hits anything that is ancient from the past, it'll replicate it from the past, like a dinosaur egg or something.
All right. So you decide to put this material mirror somewhere in Alpha Centauri, right? And get something from the past, right?
Yeah.
Right? Yeah, good. Good. I like that.
Resonator.
Uh-huh.
Did we made something that's like a resonator?
Uh-huh.
Two of the duplicator mirrors
Mm-hmm.
facing each other.
Uh-huh.
And then when you put something in the middle, since it resonates, creating a standing wave in the middle, it makes things bigger.
It's a bigolator.
Bigger what?
Bigolator. It makes things bigger. It's a resonator.
If you curve it, it will be bigger, yeah. But if you just put plain, like plain mirrors, right? It just replicated. There will be lots and lots of things.
Oh, you didn't get a standing wave there.
Uh-huh. Okay.
It's bigger than the original object.
Uh-huh.
So it's going to be a bigger object.
It's a question. It would be bigger, like as a size, but what is correct that
something is going to be bigger.
Yeah, lots. There will be lots of like quanta, lots of protons and everything.
You don't get many tiny waves. You get one big one. That's what resonator does.
No, yes, I understand that, but okay, just one little thing in quantum theory, right? When you have the amplitude higher, right, it doesn't mean that the size is bigger. It means that there were the intensity of the field is bigger, and this means that a lot of quanta is there. There's lots.
Denser. The object is going to be.
Yeah, it would be denser. Yes, it would be denser, but not bigger.
Okay,
Denser, yes.
Denser.
So something definitely will happen. Yes, that's right. That's very interesting. Yes.
Put your arms in there.
Yeah, that's right. And you'll be bulletproof.
Maybe, I don't know, but there are lots and lots of things. And interesting enough, that kind of material mirror, actually, it can be really constructed. Like with this neutron matter, I spoke with you some time ago about it. You can produce this kind of material mirror, and what will happen? There's a lots and lots of possibilities. It's a big revolution is awaiting for us in this on this side. So it's a very interesting thing to think about. Okay, guys, good. So we'll continue with this space and time 10, and we talk about differentials and integrals. This is considered to be a complex matter, but actually it's not that complex in the beginning, at least, and we will see it, right? So what is this differential and integrals? In sometime in 17th century, so 17th, right? 17th century, or to be exact, it was in 166 after Christ, right? So somewhere at that time, the greatest physicist, one of the greatest physicists in history, Isaac Newton.
Oh, I think it was going to say Aristotle.
He is the author. Remember, he is the discoverer of these laws. Remember, laws of mechanics, the laws of motion, right? 3 laws of motion. So he discovered a thing that he called fluxion calculus. And fluxions, actually, that name, it's not used anymore, but this is what we call now differential. Differential. And why he invented this thing? Because he understood already that when working with all these curved lines, you know, this all changing times, changing velocities, changing accelerations and everything, and changing fields, the fields that changes with time and distance, he understood that he needs something that can work with very small sizes, not big. Like for example, car maybe not changing its speed like for 1 kilometer, right? So 1 kilometer scale, right? Nothing is changed. But you can press the brake somewhere in the middle, right? And then press the gas and whatever, so you can change speed. And so it's not a kilometer, but smaller sizes, like maybe 100 meters, like, or 1 meter, right? Something like this. So we need to work somehow with the small sizes and small times. Pardon me?
Oh, no, Katya asked me about this.
Okay. So some small things. And that's this guy, he invented this fluxion or differential. What is differential? Yeah, actually, differential is something like what we call now, it's delta x. Like x is the some dimension, right? Like this dimension x, like this x-axis, and delta is a Greek number, and delta x is a denotation that actually says that something small, some small interval, here or here, whatever. So this is like delta x, right? This is delta x too. So it may be different. Delta x may be different, but if we try to make it very small, we say it's approaching zero. So the size of this interval goes smaller and smaller, right? So we denoted it like denotation, like dx, which d means delta, but already approaching zero. So this idea was a really brilliant idea. So it's an idea of something that is something material, right? Maybe some size, right? But very small, extremely small, almost zero, but not zero. You got the idea, right? So it was like paradoxical thing, of course, if something should be zero or not zero. So dx is not zero, but as close to zero as you can imagine. Like if you can imagine something very small, dx is still smaller than that. If you imagine even smaller, still dx will be smaller than that. So the smallest of anything, but not zero. Interesting enough, right? So this is differential. And dx is not equal to zero, but dx is smaller than anything. Anything that not zero.
Why is it 2 less than sign?
Why what?
Why is it 2 less than signs?
I didn't get.
Намного меньше знаков, спрашиваю. Про намного меньше.
Oh, yeah. What's the term for this, by the way? Antosha, maybe you know?
Significantly less, I think. I can't recall.
So this is like smaller than, but two of them, it's like double. Is that smaller, much smaller, greater, smaller than, very small. So the x is an interval, not zero, but smaller than anything you can imagine. And interesting enough that you can work with this thing because x is any variable, right? So it may be dx, maybe dy, right? Maybe dz, right? Whatever. They're all small amounts, and you can apply them to anything which is small. And you can work with smallest thing you can imagine, but still understanding and thinking about that's like a real thing. So dx is like x, but very small. Like y, dy is the same as y, but very small. dz is like z, but very small. So you can work with it like a regular variable. You can do anything. Multiply, add, subtract, divide, make like some roots, taking roots or whatever, right? To the powers and everything like this. So that was a great invention, a very paradoxical one, but interesting enough, while Newton published his greatest work. It was called Principia Mathematica. It was about the celestial motion and everything, law of gravity and everything, gravitation and everything like this, moving of the planets and everything, and all calculated with these differentials. All the orbits, actually, since Newton, all the orbits could be calculated. He invented with this thing, this calculus, differential calculus, or just it's named right now. It's named just calculus. So differential thing allowed scientists to calculate lots and lots of things. So most of the motions, like in our solar system, now is derived from these laws of Newton and using his mathematics, his differential of fluxion calculus. So imagine, this is a very big thing. So he not only invented it, but he also applied it, and applied it in a very complex ways. Like in the regular universities do not even solve this equation which Newton solved in his work. So he published this around 1666 after Christ, right? But a little later, or somewhere this time, another guy, German, as Isaac Newton was British, another guy, German, whose name was Gottfried Leibniz. Gottfried Leibniz, who was a great philosopher and mathematician at the same time, of that time, and he was French. Oh no, German. Sorry. He was German. So he invented the same thing. He named it somewhat different, and he published a book on this calculus, this type of calculus. And actually, he blamed that. I forgot who blamed who about the plagiat, stealing the ideas, because Newton, he solved this equation and everything, but he never published anything like exactly calculus thing. He never published a book explaining how he did it. So he did it, but he didn't publish this, so make it a little secret. And Leibniz published this first, before Newton. So they were arguing for 17 years for that, and that was like historical argument on this invention of this great thing, which is called differential calculus, or analysis, something they call it. So how it works? Let's take a look. We have like coordinates, like x-axis and y-axis, right? And we have some function which is y equals like some function from this argument. This is argument, this is the value of the function, right? And we have something like this. Well, like for example, function goes like this. This is the plot, right? And now we take some point and take some x here, maybe x with the index 0, right? And then we add to it some dx, some differential, small one, right? So it's almost 0, but something. So we come to some other point, which is not exactly x, but very close to it. Not exactly x0, but very close to it. So when we try to find out the value of the function, so value will be different too. So this value is y0, right? And this thing is called dy. So this point is like this. So this is close to 0 but not 0, and this is close to 0 but not 0. So we have that picture. If we take a look at this, from this point to this, we can put something like approximate, close to triangle, something like this. So this leg this size of this leg is dx, right? And this dy. You understand, right? Huh?
Okay.
This leg of this triangle is dy, this is dx. This is dy, this is dx.
They just draw it better, I'll explain it to you.
Oh, okay, yeah, I think I
You got the idea, right? So
Yeah.
here is the angle, which we call alpha angle, right? So if you remember the definition of sine and cosine, right? And here, yeah, and here this thing is this hypotenuse, like we denoted it like ds. Again, it's very small because both of the legs are small. This is small too. Also close to 0, but not 0. So try to imagine the power of these things. It's very, very small, and still we talk about this like they are real numbers, real values, real variables. But it's very, very small. Also, there's a term for this they call infinitely, but it is called infinitesimally small. It means goes to 0, approaching 0. That term. It's a little long, but like infinitely small.
Small.
Infinitely small. So now look at this triangle. If you remember this sine and cosine, right? So you may say that sine of this alpha is dy divided by ds. Look at this. This is definition simply. This is a definition of sine function.
We can't really see it because of reflection.
Really?
We can't see the x because of reflection, yeah.
Okay, can you see this?
Yeah, here we'll see it, yeah.
It's cosine is dx divided by ds. This is dy divided by ds, and here is dx divided by ds. Sine and cosine. And now we do that. We divide this by that. So sine divided by cosine. Sine, you can see this, right?
Yeah.
What I'm writing. Sine alpha divided by cosine alpha is this divided by this, right? So it is dy ds divided by dx ds. You got it? And if you remember how to divide one fraction and another, it will be dy dx ds divided by ds. You understand this step? And this equal, because ds we can, of course, it's 1, right? We get it dy divided by dx. And there's a definition. Sine alpha divided by cosine alpha is actually called tangents. How it is called?
Yeah, tangents.
Tangents. Tangents. This is just definition of sine divided by cosine. So, in short.
Tangents, sorry. Yeah. No. Tangents, yeah.
In short, we have this, that tangents alpha is dy divided by, by dx. So take a look what we're having here, right? It's a very important thing, just try to remember this. If you have any function, y as function of x, right? So y is value, x is argument. You can find any point on this and draw this small triangle. It's almost triangle because this is curved, right? But when you make it really small, this part is like a line too. It's linear too. Almost triangle, but not exactly.
Curve is round, but it looks flat to us.
Yeah.
Same thing here.
It's not that wrong. Okay, Antosh. So we have this tangents alpha, dy divided by dx. Take a look. What is this? If you remember this, the speed of change. Remember? Speed of change.
Rate of change.
So, rate of change. Yes, rate of change. So, this is rate of change y. Y is changing, right? With the x is changing. So, it's rate corresponding to change of x. Change of value y corresponding to change of x.
Then,
yes.
In this particular case, again, the reflection is killing that fraction.
This one?
Yeah.
Oh, I'm sorry.
If you just move it to the right a little bit, the fraction itself.
Yeah. Okay. So I'll rewrite it. So dy divided by dx. It's a rate of change corresponding of change of argument of x. So how fast y, the function, how fast y is changing when we change x? Anything. So this is the speed or rate of change. Rate of change of function relative to change of argument. If this x, if x we change by t, right? For example, t here, so here will be t. So this is a regular rate, right, in time. But with the x we have, not in time, but with this any dimension. X or maybe y, whatever. Actually, if it's y here, what will happen? Also not alpha. If it's y, dy divided by dy, what it will be? 1, right. So 1 is a constant, so no change. Nothing is changing. 1 is still 1, whatever you change. So we have this thing. This thing, it is called this dy divided by dx, or whatever argument it is. It is, the other denotation is I y prime, right? Antosh?
Yeah.
Y prime, and here we usually show what is here, just like an index. So y prime by x, it is the same as this. This is just another denotation. This is index, so do not mix it with the argument. Argument is here, and here is index. Why it is index? Because there may be two arguments, like x, y, right? Maybe function of two arguments. No, not y, sorry, z, right? Like z. But this thing is by x, so here we use index x. And this thing is called derivative. So rate of change is called derivative.
Derivative.
No, derivative, okay, sorry, derivative. So remember this thing, because this is the main thing, and you will see it a lot in many applications of mathematics and everything. This is the center differential, right? Dx or dy or whatever, and derivative. So these are main things in this differential calculus or analysis, they call it also. So now let's try to find out how it goes mathematically, all these things. It's pretty easy in many ways, but sometimes it goes a little more complex, but in many ways it looks like very easy. And usually differentiating or taking derivatives is much easier than taking the other way. We'll talk about this. So first of all, we'll talk about simple things. Like, for example, we have a function, like first example, we have a function y equals like some constant, like 5. This is a function too. There is no argument, you see, but still function. Y is always 5. What function it is? If you have x, you have y, here is 5, here is like 1, right? And y is always 5. So this is the plot of this function. Whatever x is, this x, here, any x we take, we always get 5. So this is constant, it's called constant function. And now we try to change x. What do you think the rate of change of y will be in this case? What do you think?
What's the rate of change of y? Look it down. Take a look at the graph, that's it. Oh, there's no graph.
What do you think? How y is changing when we're changing x?
It's changing by 0.
So no changes, right?
Yeah.
So what the derivative will be? What do you think?
0.
0, right? Exactly. It's not changing. So it is 0, right? So you understand? No change, and the graphic is like this line, right? So if we put here any other constant, like a, and this is like constant, right?
A. AX.
Any a, not 5, but a. Would it change anything?
A is a constant.
Here a, right? Here x.
No,
And
no.
constant means it's not changing. So any a, so a constant, so derivative from constant function is 0. That's first thing we should remember. Now second, we have that simple function, y equal x. Y equal x. So 0 x 0 y here plot here a dot, right? Another x1, the y will be if x is 1. How will what value 1? If, like for example, 5, what y will be? Huh? 5. So we have here dots, right? And this is the straight line, and here goes the same thing, because like -1 is -1, right? So this is line like this. Now let's try to find out what the derivative will be in this case. We calculate like this, like what is we have y is x, right? Now let's try to find out would be the derivative, like derivative. It is, by definition, it is dy divided by x, right? And dy, when we calculate like this, in certain point, like for example, certain point x, right? At certain point x. If we have certain point x like x1, certain value of x, y will be
Y1.
no, not y1, yes, y1, but because x equal 1, yeah, x equal y, it's x1 too, right? Equal this. So we have the same thing for y. So dy we may write, so like x1 minus bigger from the smaller. So x1 plus dx, because y always equals x, minus x1 and divided by dx. Let's look at this. What is this? What is this? You can see this?
Yes, yeah, we can see that.
So we're just calculating what is dy in this case.
Can you cross out the 2 dx's?
No, not while there are.
Oh yeah, it was send this.
It's not the bracket. It's addition and subtraction.
This is x1.
Not while there are other members.
This is x1 plus dx, right? This is y1 or equal x1 because the function is this, right? So here is x1 and x1 plus dx. Here it is. We say the function is y on this with this argument x1 plus dx. Argument is changed. You see? This is function, still the same function. Here is y from x, and here is y from x plus dx. Got the idea?
Just write it down. I'll explain to you.
We will write it maybe a little differently. Here's 1y, y1, and here is y2. The first equals just x1. The second, because x always equals y, this is x1 plus dx. It's the same function, just different arguments. One argument is x1 and the other is x1 plus dx. But still, because the function is y equals x, it's the same thing, right? So y1 is x1, y2 is x1 plus dx. And then dy we calculate like y2 minus y1. And this is exactly that. All this. Here it is. y2 minus 1. This difference. This interval. Good idea? Eh? Trying to?
Sort of.
Sort of, okay. Sort of. Just, okay. I'll repeat again. Just, you are changing argument. Argument is x. We're taking one point, x1. This is the point. The change is we're adding to x1 some dx. Changing. So, argument is changed this interval, right? And this interval is actually dx, right? Because we change it from this to this, and difference between this is dx only. So it is dx. This is dy. This is dy. But dy is 2. y2 means minus y1. This length of this thing. So y2 minus y1. So this one. And this is also dy. Because it's small. This small and this small. This almost 0, this almost 0. But still, it's y2 minus y1. So you may write y1, or sorry, y2 like y1 plus dy. Because this is dy. Right? So just that, you should, it's not easy in certain way, because there's dy's and it's a little confusing, these things, but try to understand that all these dx's and dy's are just regular, like regular numbers. You work with them like regular values, regular variables, but they are very small. They're infinitely small, but still you can work with them easily, like they're regular things. So you look at them, they are regular intervals, whatever, you can picture them and everything. It's very easy to look when you look at this. Just a little confusing because all these dx's. But you'll get the idea a little later with this. So anyway, so we write this, then we return to this. So we have this thing. dy is x1 plus dx minus x1. And of course it is dx, right? At the bottom. It's just dx. And divided by dx. So what will be the result?
1.
1. Exactly. So if you have this function, y equals x, or they call it linear function, a simple linear function, the derivative of this will be 1. If you have some similar thing, like for example, we multiply this function by a, and a is constant, like 5. We will have a here, and a here. So we have a here. A, and this is common multiplier, right, Antosha?
Yeah.
Common multiplier. So we can put it here and it will be the same. And the result will be not 1, but a. So if you have constant before argument, so that kind of function, the derivative will be just a, constant. What it means? It means, remember this picture of this function. It is linear and straight, right? It means that the speed is not changing. The rate of change is constant. It's not zero, but it's constant. And constant equals to a. This one. Constant may be 1 in this case, or maybe r in another case. So if r is more than 1, you will have picture like this. So the speed is changing faster. The speed is bigger. The rate of change is bigger. So the only thing, and just explanation, you'll talk with it later and everything. But all you have to remember here that this function, the derivative with this, with linear function, will be equal to a. That's what you should remember. And try to play with this too. Now, a third example. We have quadratic function, x squared. X squared. Right? So again, let's try to calculate this thing. So again, dy divided by dx, and y now it is, again, y2 is, y1 is x1 square, right? We take some point x1 and see what would be y1. y1 will be x1 squared, and y2 will be x1 plus dx, and both of them squared. You see that, right?
Yeah.
So the same thing. So we take y2 minus y1 divided by dx, and you see this, because this is x squared, right? So we have x1 plus dx squared minus dx, also minus x1 squared, and divided by dx. Can you see this? The last one, the result? We will just write this here, right? That's all. Because dy is y2 minus y1. I'm not sure. Can you open these brackets? Do you know how to open these brackets when it's squared?
A equals b squared. Do you remember the formula?
Oh yeah, it's good to see first.
No.
Okay, if you don't remember, just do that. Just square it is, right? It's x1 dx multiplied by the same thing, right? What is square? X1 plus dx, right? And multiply them. So 1 multiplied by this, then to this, then to this, then to this. And the result will be x1 squared, right? Plus 2x1 dx and plus dx squared. Remember that formula?
Yep. Yeah.
Okay, so let's try what we have as a result. So we have here x1 squared plus my x1 squared minus x1 squared, remember from here, right? Plus 2x1 dx and plus dx squared, and all divided by dx. And let's take a look at this, what we'll have here. This is minus the same thing, right? This divided by dx will be 2x1, right? This part divided by dx will be 2x1, and also this dx plus dx squared divided by dx.
Say.
That's dx.
There dx, right. So it is plus dx plus dx. And now we have this, right? And do you compare? We need the real value for this. Real value. If you're really concerned about real value and not these zeros or the x's, about real value for y, it will be only 2x1 because the x is almost 0. And this is what we do when we calculate derivatives. We just throw away, we just waste anything that is really small. Almost 0. Maybe not 0, but almost 0. And the result is 2x1. That's what is done. So, and it means that with this thing, it equals 2x. Almost the same thing if you calculate for this function like x to the power of n. You can like suggest any clue. What would it be? What do you think?
No.
You see the index. You see the power comes here, right? Like a multiplier, right? And the power of this is less than power of 2. It's 1. Here is like 1, right? 2x to the power of 1. It's the same to x. So what do you think is here?
What do you think is there? You trying to answer?
Any guess?
HX. Did the HX.
What?
Oh, sorry, that's an N. Did the NX.
NX looks closer, but you see, it's just smaller than this, right? It's still the power, but just 1. Here is 2. Here is 1.
In x squared, how much is the power less?
What?
How much do you decrease the power when you take the derivative of x squared?
You see, the power is less by 1. You see? 2 and 1. So it is. Oh. Okay, good. If you wanted to say that, yes. This is the formula for the this power function with the power of n, right? So this, try to remember, because these things are very useful. These formulas are very useful in differential calculuses. Also, I would not derive it, but I'll tell you, and I think you should remember that because it's very often uses. Very often uses. So it was example 5, right? Example 5. Okay. Y equals sine x. Derivative is cosine x.
Oh, it's the opposite when you go.
Yes, yes. If y is cosine of x, derivative is, any guess? Huh?
Did a sin x.
Almost, but not. Minus sine x. Minus sine x. Now, a very interesting function, which is called exponent. Exponent. It's called. It is pronounced e. This number, Antosh. E. E to the power of x. And this, I should say a little more about this. E is so-called Euler number. E. Euler is a name of Leonard, I think with H. Leonard Euler is one of the big scientists. I forgot what century it was. I think it was 19th century. Or maybe, yeah. Huh? Yeah, and he found out this interesting number, which is close to 2.7 and some numbers after that. 2.7 and something long. It is a rational number, so-called, so it's very long, infinitely long. It's 2.7. It's a very interesting number, and it has, by itself, it has very interesting features. Like, for example, there are connections between other magic numbers, like pi, like imaginary unit, remember I? There's an interesting connection which is called, again, Euler, I think identity. Identity? How is it called? Yes, identity. It's called Euler identity. You can see here, right?
Yeah.
E to the power of E pi. E is imaginary unit, and pi is pi, right? E to the power of E pi equals -1. Look at this. So here's Euler number, here's pi, here's y, imaginary, right? And this power gives you -1. Magic. We'll talk about this later when we come to complex, so-called complex numbers, but this is a very interesting identity. But Euler himself, that was derived later. Euler himself, I think he found this interesting thing, that Euler number equals to like 1 plus by n when n approaching infinity. So imagine 1 divided by n and n approaching infinity. 1 divided by n approach what number?
Infinity.
Huh?
No, 1 divided by n.
1 divided by n.
1 by infinity, what do you get?
1 over infinity.
Yeah,
which
1
is-
over infinity.
1 infinity.
Which is... Yeah.
Which is?
But the larger you get, what happens?
Small.
Which is?
Smaller. And if you get to infinity,
It'll be like minus infinity.
Oh.
Zero.
0, right? So this goes to 0. So this together, 1 plus 0 goes to 1, right? Approaching 1. And then to the power of n approaching infinity. So 1 multiplied by 1, almost by 1, infinite times. But it's not 1 exactly. It's 1 plus something, right? Very, very small. But because it's multiplied by many things, interesting, it was calculated, it equals this magic number E. Interesting, right? So, magic number. Also, there's other interesting thing, like just for you shouldn't remember that, but E equals to sum. You know the sign sum?
No.
No? This is mainly the sum of many things with the index from 0 to, like n, index n, from 0 to infinity of this thing, n factorial. This sign means, this exclamation sign means factorial.
Which means?
You know what factorial is?
No.
No? Huh?
You said, oh, no, never mind. I think I know. I think n factorial would be at n times all the numbers before n.
Yeah,
exactly.
exactly. Right. So many of these things summarized, they gives to this number E. Interesting enough. It's very not obvious thing, right? And this, so it looks like that, like 1 divided by 1, because factorial of 0 it is 1. Then plus again 1, because factorial of 1 is 1 again. Then factorial of 2, then plus 2 and 3 How much would it be factorial of 3?
6.
6 plus blah 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 blah. It's a very fast growing number, so it is going very small, but still it gives this Euler number. So
Euler.
Euler. Okay, so pronunciation is Euler. Euler number. Okay, Euler number. So any guess what will be of this derivative of this fantastic function e to the power x? Derivative will be derivative, huh?
X to the power of e.
Okay, guys, any
Yes. What's yours?
ideas?
Minus x e to the e minus 1.
No, guys. Okay. I'll stop doing this because it's no way. I would not go into derive it. You may try with your father, but it will be the same thing. The same function.
Oh, that's right. Because it's basically 0. It's 0.
No, it's not 0. E is about 2.7. It's a number, 2.7. It's a constant. E to the power of x, and okay. So
Interestingly enough, this kind of connects with Avogadro number.
and interesting. Yeah, right. Avogadro. Okay.
Mass equals mass in grams.
Okay. Avogadro number. Still, it's the number. It's still 2.7.
What I'm saying is,
Not big enough. It's about around 3.
rate
Around 3.
which the function equals.
Okay. So and you understand, like if you go, if you try to go derivative more and more, like if you take, like for example, derivatives of this like three times, it's named like this. Derivative of this one, what will be? From this derivatives, it is this. But the double derivative, what will be? What do you think? Try to find out the rate of change of this now. Of this.
I think it's still ex.
Still the same thing. So whatever you, how many times you make a derivative here, still be the same thing, right? Still be the same. And try to this. Like if we try, okay, from sine, the derivative is cosine, right? And we try to make derivative from cosine. What will it be? Minus sine. And another sine goes to cosine, it will be minus cosine, right? So we still have and minus cosine, then again and again, after 4 times I think or something like this, you'll come to cosine again, to sine again. So those are repeating each other too, but with certain steps. So these are things about derivatives, some interesting. And this formula try to remember. Antosha, remember them, I hope?
Which one?
All these for sine, cosine.
Yeah.
So you remember that. So and try to make guys to remember. Now,
Speak English before I forget that.
yeah. Now let's go to other thing. Like for example, let's start from the another. So we'll continue examples further, right? Now we'll talk about integrals. And they called also indefinite, right? First of all, talk about so-called indefinite integrals. Integral is inverse derivative. Or inverse, simply inverse, right? So inverse derivative. So if we have function like ex and we have derivative ex, right? And we try now to go back. Then we go to derivative here. Now we're going from derivative to the function. We know the derivative. What will be the function for this derivative? What do you think? Just go back.
Y equals minus.
No, if we have this, we have this. The derivative of some function is e equal x, e to the power of x. What will be the function, original function, if we return?
Minus y equals e to the power of x.
Where'd you get the minus?
Because like.
Remember, from here we comes to here, the same function. Now we try to find out original. We don't know this, but we know this. And we want to know which function was actually processed to find out this. Huh?
Y equals EX.
Yeah, the same thing. It's no changing here. So, and this back function, it is denoted like this, like this. So we have derivative, and we try to find out the original function. This is how it denotes, the denotation of this. This is called integral. This is actually sum, just by the letter S, just pulled like this. So this is integral, like sum. And this is also dx here. That's like the notation. We'll talk about it later. So just the notation for this, and this notation is called integral. All you should understand about integral here for now, that it is inverse derivative. Inverse derivative. So if you try to go back with this processing, not to make derivative from the function, but to find, we have derivative and to want to find the original function. So this process back is called integrating, and it's a little more complex than finding out derivatives, differentiating called this process, the first one. But still, it is doable.
And by a little, then it means a lot.
Okay, so it's still doable, and we can try to find out like the simple things, right? Like first, let's start from the beginning. Okay, like for example, we have derivative. Okay, we'll go back. We'll have derivative equals to 0. What will be the original function?
Y equals 0.
It may be 0, right? Yes, but a little more complex.
Which function doesn't change?
Yeah, which function doesn't change? Remember this? Huh?
Yes. Which other?
The Y.
1.
What?
Y equals 0. It doesn't change.
Yes.
Yeah.
But more generically. What else?
More generically, yes. 1. Another function. 5,
Yeah.
6, 7, 8, 9, 10. Huh?
Yes. Any number that doesn't change. And we call those numbers instead of the name. Constantine. So y equals
Constantine.
constant.
Oh. Yeah, y equals 5 or 6 or
Y equals constant.
how we call number that doesn't change?
Constant.
Constant, right? So y is constant, or like a, right? For example, some a. Usually constant. So some constant. So y equals constant, then derivative now. X now, like derivative is x. Imagine that original function which we find derivative and it gives you x. What do you think? What function can this be? Or maybe easy. Not oh yeah, okay.
Y equals X.
Huh?
Y equals X.
Y equals what?
What is the derivative for y equals that? Would be 1.
Okay, maybe let it be like some constant, like maybe 5. What function will give you 5?
Yeah, y equals 5.
Give me 5. Okay, there is 5. Which function can give you 5 as a derivative?
Then the kids wouldn't know. They're confused.
Yeah, right. Okay.
But you
If you make a derivative from x, what would you get?
A constant.
They're confused. They don't know.
Okay. So for 5 it will be 5x. Because if you have 1, so the function is x. When you make derivative from x, you get 1. If you have here 5, you give here 5. You get here 5. If you have something like this, it will be ax, linear function. Okay, it's a little confusing because it's new, right? But it's you'll find out it's simple. Now, for example, you have like x. Which original function? Huh? X squared. And something else, because if you try to x squared, you'll get 2 here, right? Remember? If you try to calculate derivative, you get 2 here. And you have only x.
X divided by 2 squared.
X divided by 2 squared.
Very
close, but wrong.
Yeah. So you understand that to make derivative from x, you get 2 here, right? But there's no 2. So what you should...
X squared divided by x.
What is the x squared divided by x?
X.
It's x. That's right.
Oh, I was thinking of that. I thought it was dumb.
It's x squared over 2. You were wrong.
Oh.
So you just... Okay, you understand it.
No, you said x over 2 squared.
That's x over 2. And then that's what... Oh.
That's
Right.
x squared over 2.
This is just multiplier. It doesn't change anything. You have it multiplier. It goes like outside. And when you try to this, you get 2. So 2 divided by 2 will 1, and x will be power 1. The power 1. So this derivative gives you this original function. And to make it formula, like total formula for anything, for any power, we can get this. If you have x to the power of n, which original function it is?
Wait, x to the power of n?
Yeah. Power should be probably lower than n, right? Because this original function. Oh, sorry, higher, of course. So, plus, because when you take derivative of this, you'll get n, right? From this, get n, because the power is less by n. And also this multiplier, you get this multiplier, so you should divide it by n plus 1.
What about the constants? Plus c.
Constant, yeah. Yes, you can explain this, yes, a little later, okay? Yeah. Okay, I think it's enough for today. Any questions? I wanted to get more, but it's too optimistic.
Yeah, I think you already.
Yeah, already over.
Much as you should have.
A little over confused. Okay, guys. So, any questions for this?
No.
Does it look complex or not that complex or mix?
It was complex.
Complex. Okay, you'll work a little more, and you will see that this part a little not that complex. So integration is just inverse to derivative, to taking derivative. That's what you should know. Okay, and let's talk about exercises, right? Home exercise. You ready to write?
Wait. Ready?
You ready? Okay. So the first, try to define a derivative of vector function. You'll get explanation later what is vector. Vector is a function which have argument like regular argument, like x or y or whatever, but as a value it has a vector.
Wouldn't that be just a gradient?
Okay, Antosha,
That's a gradient, right?
just that's a question, okay?
It's a gradient.
That's not gradient. If you want to, not if you're talking about many argumental, I'm asking just one argument, x, for example.
Right, but
it's not a gradient yet. Gradient is about many multidimensional spaces. You may talk about this. I'm not against it. We'll talk about it a little later. Okay, so just define it. Okay, how to just let them to understand this. Question second. Define means just put a formula, whatever. Think about it, right? Second question. The distance as a function of time, s, distance as a function of time, is changing. You may write even x here, but anyway, it's changing with that kind of formula. 9.8 t squared divided by 2.
What are we supposed to figure out?
the velocity.
Make formulas for velocity. This is distance. For velocity and acceleration. Just think about what is velocity, what rate of change is it, what acceleration is the rate of change is it. Think about it and put formulas for velocity and acceleration. Got the idea? Got the question?
Yeah.
Okay, formulas. Put formulas for this. And now the last one, you should think about this. Calculate. This is the 3, right? This is 4. Calculate how hard in force, so make a formula for force, which happens in a shot when you have, like, for example, you have the tube in your kitchen where the water is going, and water has density 1 gram per centimeter cube, right? It goes with the speed of v. V is velocity, or speed, like velocity. Velocity for the water. Antosh?
Yeah, I'm listening.
Okay, and here we have this faucet, or crane, how you call it? The kitchen.
Tap.
Huh?
Tap.
Tap, okay. Tap B or tap P?
Tap.
Like this?
Yep.
Okay, and you turn it off, like right away. So the water is going and then just bam, stopped. What will happen? Maybe you know, if you very fast turn off the tap, what will happen? You ever did that?
There would be shockwave.
You have a shock. Actually, it's a pretty sound. It's a big sound, a bam, like a hit. Sometimes very hard one. Sometimes the whole tube becomes like vibrating. It's a very loud sound. So try to define a formula using the formulas of the laws of Newton, laws of motion, and try to derive a formula for this. Rho, velocity, and actually I give you the speed of sound. You will need speed of sound. It is about 1.5 kilometers per second in water.
Okay, wait a second.
The sound in water goes with the speed 1.5 kilometer per second. So try to, with the help, of course, you probably would not be able to do it, but just a little, try to work with the laws and with these things that we work together, because can be derived. This formula for the force, and you may use your own tube. Like what size of the tube? Like about 1 centimeter, right, or something like this. 1 centimeter wide. So you may use this.
No, it doesn't. It's numbered.
So you have the density of water is 1 gram per centimeter cubical, per cubical centimeter. The velocity, like v, like for example, I don't know, whatever, like velocity, maybe what velocity we'll use?
I don't know. 1 meter per second.
Okay, 1 meter per second. You may find out how much would be in the velocity of your car, like 1 meter per second, for example. But you try to derive the formula. The speed sound in water is 1.5 kilometers per second. Kilometers per second. So this is the last question for this. Try to do it. It's fun. Trust me, it's fun. Okay. Any questions? No. Okay, guys. Okay, see you next time, guys.
I didn't love you.
Yeah, I love you guys.